Hello, everyone. Welcome to the second day. Before starting, the organizers, they asked me to tell the speakers from yesterday to look at Discord. There are some questions over there that you should answer. So look at Discord, and yeah, there are more questions for our talks. And now we can start the second day. So we're very happy to have the second invited speaker, Dakshita Khurana. She's currently at the UIUC, and it's very interesting because she started from classical cryptography, and then she moved to Quantum, and she has very beautiful results on unclonable cryptography, and now also in this like low end assumptions in quantum cryptography.
Thank you, Alex. So today's talk is going to be about understanding cryptographic hardness in a quantum world, or a cryptographer's guide to sleeping better. This talk is going to be based on joint works with two joint works with my student Kabir Tomar, who's at UIUC. Before I get started, I just want to thank the organizers for organizing this amazing conference, and thank you so much for inviting me to speak today. All right, so let's get started. So humans have relied on ciphers for millennia. Assumptions and classical cryptography have had a very tight relationship over the years. It all began with people trying ad hoc, insecure designs that would often get broken. And then modern cryptography came along, and modern cryptographers began to rely on the hardness of very specific mathematical problems, such as RSA, factoring, Diffie-Hellman, and so on. Even more recently, we've begun to club many of these problems into generic assumptions, which can be instantiated from a variety of specific mathematical problems. And we've been using these generic assumptions to build beautiful cryptographic primitives. I like to use this slide by my advisor, Amit Sahai. This slide is about the landscape of assumptions in classical cryptography. And what he says is that we've used these beautiful seeds of RSA, factoring, oh yeah, this works, Diffie-Hellman assumptions, learning with errors, multilinear maps. There's this whole abundance of hardness that comes from mathematics. And we use these as seeds to plant these beautiful flowers and these gardens of cryptographic primitives, and like public key encryption, multi-party computation, and so on. And ignoring that there exists some information theoretic cryptography, but most cryptography that's actually also being used today relies on some or the other hardness assumption. And the goal in classical cryptography for all these years has been to try and base crypto on the weakest possible generic assumptions. And one thing that we know for sure in classical cryptography is that one-way function, which is a function that's easy to compute in one direction, hard to invert, is necessary for almost all of classical cryptography. So let me just explain what a one-way function is in a bit more detail. This is an efficiently computable function f, such that for a randomly uniformly chosen input x, inverting f of x is hard. So pictorially, you have going from x to y is easy, y to x is hard. And mathematically, what this says is if the adversary is given y for y equals f of x, where x is sampled at random, then it's hard for the adversary to find any pre-image of y. This is an assumption that we make, that like all polynomial time adversaries, which roughly corresponds to all real-world attacks that can exist, cannot invert this function. So do one-way functions actually exist? Unfortunately, we don't know the answer to that question. We have a lot of candidates, so we've been able to get by pretty well by having a whole bunch of candidates, and I've listed only 3 here, that give rise to one-way functions. For example, the hardness of factoring implies the existence of a one-way function that is hard to invert as long as it's hard to factor products of large primes. Can't hear me? And if one-way functions exist, then we know that P is not equal to NP, which poses a major barrier to actually trying to prove the existence of one-way functions. Because if you could prove that one-way functions exist, then you'd be resolving what is the biggest open problem in theoretical computer science right now, which is the P versus NP problem. So this is a really difficult question. We've been getting along. And I just want to point out that even proving that P not equal to NP may not suffice to demonstrate the existence of one-way functions. All right, so this has been a major problem. Classical cryptography cannot exist unless one-way functions exist, and we don't know if one-way functions exist. So we look at hard mathematical problems that people have been trying to solve for decades and have failed, and we use them to build cryptography from them. And there's this adage that cryptographers seldom sleep well, was said by Silvio Micali, and just the existence of all of classical cryptography is basically in a crisis all the time. Now, how to sleep better? Well, start working on quantum cryptography. So the question is, does quantum cryptography exist? It turns out that one can relax or even remove the assumptions that one needs to build crypto protocols if we start using quantum resources instead. So participants are quantum, they use quantum channels to communicate, and this makes it sometimes possible to use these beautiful properties of quantum information instead of mathematical hardness assumptions. And the prime example of this for many years has been quantum key distribution, which classically is impossible, but using quantum resources, this becomes possible. And it's, in fact, secure against adversaries with unbounded computing resources. So what I'm trying to say is that maybe in quantum land, there are ways to sleep better because maybe you don't need one-way functions. And of course, Tomoyuki gave a wonderful talk about this yesterday. I will be referring to some of those things today. But for today's talk, I just want to emphasize one difference between post-quantum and quantum cryptography. So in post-quantum cryptography, participants are classical. The adversary, on the other hand, may be quantum. So here the goal is to build protocols that we can implement today on today's classical devices, but that remain secure against a future quantum adversary. And this actually requires at least as much hardness or structure, if not more hardness, than classical cryptography. So for example, for post-quantum cryptography to exist, you need at least that post-quantum one-way functions exist, which are one-way functions that are classically computable, but secure against quantum attackers. So quantum attackers cannot invert them. And I want to draw a distinction of this from quantum cryptography, where participants themselves are quantum, and the adversary is also quantum. And this is the land that potentially requires less hardness and less structure than classical cryptography. So in the rest of this talk, I will describe some examples of how to get interesting results in this land without relying on assumptions that are necessary for classical crypto. Okay, so first of all, it looks like once we have quantum computers, QKD is possible. You can do cryptography information theoretically, no need for assumptions. So is this it? Is this the end of the story? And as you've already seen yesterday, sorry, get to the right point. Yes, cryptography is actually about a lot more than key distribution. So for example, a cryptographic commitment is an important primitive that allows a committer Alice, who has a secret message M, to virtually lock this message in a box and send this locked box over to Bob, such that this message remains hidden from Bob at the end of the commitment phase. Later on, during a decommitment phase, Alice can give Bob the proverbial key to this box that lets him unlock it and recover Alice's message. And the guarantee is that at this later point, this message cannot be changed. So Alice cannot open her commitment to anything that's different from the message she originally committed to. So this is an important, okay, something is wrong. Sorry. Okay, yes. So in reality, what you actually have is Alice and Bob interact, send each other a few messages, do some encrypted communication, and so on. And at the end of this, they end up with this transcript that is called the commitment to message M. And in a later phase, analogous to sending the key is this message. This could even be some more rounds of interaction between Alice and Bob that end up revealing the message M to Bob. And unless Alice initiates the decommitment phase, the message should remain hidden. Okay. So this is a very fundamental primitive. It's very useful. And I'm going to give you one more example of another primitive that's both useful and actually also ends up using commitments. So this primitive is called secure multi-party computation. This allows 2 or more players that have their own private inputs to securely compute joint functions on these inputs while hiding all secrets about them. So for example, in a 2-party setting, Alice and Bob have their own private DNA data, and they want to test whether they're related or not. And neither of them wants to actually give out all their DNA information to the other one. So what secure computation allows them to do is to run a protocol where they each encrypt their DNA, and they talk to each other a few times, sending messages back and forth. And at the end of this process, the only thing they learn is whether they're related or not. And they recover no other information about the private inputs of each other. One can also look at this in a more general multi-party setting, where there are many players that want to compute some function of their private inputs without revealing anything to anyone else except while only learning the output of the computation. Okay, so this is a really useful primitive. It's being implemented all over the place these days in industry. There's a bunch of startups doing this. If you've heard of threshold primitives, they're basically a form of MPC. So this is really a broad, general, and highly useful cryptographic primitive. And the reason I gave you these 2 examples is because they have a very interesting history in the quantum world. So originally, a while ago, commitments were believed to exist with security against computationally unbounded adversaries without the need for any assumptions, as long as one used quantum resources. So there was this belief. It showed up in a few papers. See, for example, this paper. And assuming that these types of commitments exist, there were also papers that said, oh, quantum MPC can exist. So if commitments secure against unbounded adversaries exist, here's a way to use them to do multi-party computation. And there were these papers. And some years later, it was actually discovered that commitments cannot exist with security against unbounded adversaries, period. So there do not exist any commitments that remain secure if you give Alice and Bob unbounded computing resources. So you do need to make some type of assumption or some type of bound on the amount of computational power that you give to your participants in a commitment or even an MPC protocol. So this was in independent works of Mayers and Low and Chow. Okay, so people believed commitments exist, then they realized, well, they don't exist unconditionally, we need to work harder to get them. And so the main open problem that I want to talk about in today's talk, and that's been a focus of research for the past few years, is under what hardness assumptions do commitments and MPC exist quantumly? So the goal is to try to understand the sources of mathematical hardness that give rise to cryptography in a quantum world. Again, I'm going to give you a few examples in the rest of this talk. Let me first start with this example of getting better secure computation /MPC, which is this primitive I told you about, where parties can collaboratively compute functions of private inputs while only revealing the output. So in a joint work with Bartosek, Coladangelo, and Ma, and in a different joint work of Grillo, Lin, Song, and Vaikunthanathan, it was shown that computationally secure classical commitments imply secure computation if you can use quantum resources. So commitments are sufficient for building secure computation protocols. And moreover, one-way functions imply these types of commitments. So what this shows is that one-way functions are sufficient to build secure computation with quantum participants. I want to point out that these works actually showed that black box use of commitments is enough. And this is something that is uniquely quantum. So there is quantum advantage here in that the ability to do secure computation with only black box use of one-way functions is something that is impossible classically, but becomes possible when using quantum resources. Okay. I also want to emphasize that even though these works used classical commitments, subsequent works, in particular that of Anant, Kian, and Yuan, showed that you could use quantum commitments. So if your commitments were using quantum resources to actually implement the commitment, that would also be good enough. And the reason that I want to, before moving on, I just want to point out that it's open to understand whether one can use one-way functions to build secure computation protocols where parties do not have to send each other quantum messages. So ruling this out, proving this is basically open. There's been a few partial results along the way, but to my knowledge, yeah, this is an important open question. Okay, so I do want to move on actually to my next example, but I want to use this slide to emphasize that commitments seem really important. If we had commitments, we'd be able to do multi-party computation, and one-way functions give us commitments. So is this it? Are we done? One-way functions are necessary for classical crypto. The point is they may not be necessary to realize quantum crypto. And so what assumptions can we use to build better commitments in a quantum world? Here by better, I mean use assumptions that do not necessarily imply the existence of classical cryptography. So going into quantum land, it is known that actually relative to a quantum oracle, quantum commitments, and in fact, a more general pseudo-random states and unitaries can exist even if BQP equals QMA. This was due to a result of Kretschmer. It is also known that relative to a classical oracle, quantum commitments or pseudo-random states can exist even if P equals NP. This is due to a result of Kretschmer, Kian, Sinha, and Tal. The way that I interpret this philosophically is that quantum cryptography could be based on assumptions that are mathematically weaker than the existence of one-way functions. So there's this beautiful landscape of classical cryptography with the flowers and the gardens blooming on nice seeds. And there is this ocean that has quantum crypto systems floating around in it. But we don't really know what concrete assumptions to ground them on. I do want to mention here that there are these conjectures that sufficiently random circuit gives rise to pseudo-random states and unitaries, but we haven't been able to analyze these or ground these in like other problems that we know how to answer. So I'm going to be discounting those for the purposes of this talk. Okay. And so we've been using all of these so we've been coming up with all of these beautiful primitives in quantum land. And this is from Tomoyuki's slide yesterday. There's these really nice primitives, pseudo-random states, one-way states, commitments, NPC, EFI. They're related in various ways. It's really exciting to discover connections and relationships between them. And there's actually even more primitives that have been defined. So there's this huge graph that Tomoyuki also referred to yesterday that has all these various definitions, and this doesn't even cover many of them. So there's even more than this. Quantum cryptographic relaxations of classical primitives that we've come up with, and we're exploring how they relate to each other. But a major objection that one could have to this entire line of work, and I think this would be somewhat valid, is that how do we know that any of these actually really exist? Do we have any concrete candidates for them that have been analyzed at all that do not rely on assumptions such as the existence of one-way functions? And this is something that I want to at least take a step towards answering in today's talk. So I want to discuss how to build quantum cryptography from certain complexity theoretic assumptions that have been somewhat well studied and are concrete and do not imply one-way functions. Okay, so in the rest of this talk, we will focus on this primitive called a one-way puzzle. I'll first define what this is and explain why these are cryptographically useful. And then I will explain how to ground this assumption in the existence of concrete mathematical assumptions that do not require the existence of one-way functions. Okay, so let's get started. So what is a one-way puzzle? A one-way puzzle is basically a way to model a quantum process that samples hard on average problems together with their solutions. So it consists of a sampler. The sampler is randomized. It's a quantum polynomial time machine that outputs random X and Y pairs. Think of X as a solution, Y as a puzzle. And there is another machine called a verifier that, given a valid X and Y pair, so something that satisfies some relation, outputs accept as long as X and Y satisfies the relation, and otherwise outputs reject. The guarantees we have is that outputs of the sampler are going to verify with very high probability. And moreover, it is actually computationally infeasible to invert a Y to find an X that will verify. So given a random Y sampled as the output of the sampler, finding an X that causes the verifier to accept is hard. Okay. Let me contrast this with one-way functions. One-way functions are different because they're essentially deterministic. There is a deterministic function that, given X, will deterministically give you Y, where Y is hard to invert, whereas with a sampler, you get these random X and Y pairs, and you cannot necessarily make it deterministic because the sampler is quantum, and you cannot pull out randomness from quantum processes. Okay, so the definition of one-way puzzles is somewhat clear. Let me just state the main technical theorem informally. This is from this work with Kabir, where we show that one-way puzzles actually imply the existence of commitments. Now, again, for the purposes of the rest of this talk, it suffices to think about commitments slightly differently than this like game where a committer commits and so on. A commitment is nothing but a pair of efficiently sampleable mixed states, rho 0 and rho 1, that are far from each other in trace distance, but are computationally indistinguishable. So no efficient or polynomial time quantum algorithm can tell whether it obtained a sample from, or whether it obtained mixed state rho 0 or state rho 1. Okay. This simplified variant of a commitment is called an EFI pair and was first talked about in this work of Bitansky, Canetti, and Kian. Although the fact that this implies commitments and is basically equivalent to commitments was discovered in an earlier work of Yan. Okay, so towards understanding this theorem that one-way puzzles imply commitments, I want to start with the warm-up exercise of proving that something simpler, which is that an injective one-way function implies a commitment. So for any injective one-way function f, injective just means every image has a single preimage. The Goldreich-Levin theorem shows that for uniformly sampled x, r, and u, f of x together with the inner product of x and r, given r, is indistinguishable from f of x together with a uniformly random bit given r, as long as x is hard to recover from f of x. So basically, the fact that the function f is one way translates to computational indistinguishability, to the fact that these distributions cannot be distinguished. In other words, any distinguisher that distinguishes the distribution on the left from the one on the right should essentially know x and gives us a way to find x. But note that by the one-wayness of the function, x should be hard to find given this stuff, right? Given f of x, x should be hard to find. And so that's what leads to computational indistinguishability here. Moreover, the distributions are far in trace distance because basically the left distribution has less entropy than the one on the right. Okay. All right, so this is the way to get a pair of mixed states that are far in trace distance but look indistinguishable given any injective one-way function. Now let's make the problem a little bit harder. What about one-way functions that are not injective? So if the one-way function is not injective, then f of x does not necessarily determine the string x. And while the two distributions are still computationally indistinguishable, they could actually end up being the exact same distribution. That's because x dot r may have as much entropy as a uniformly random bit given f of x. So what do? It's hopeless to try to convert a one-way function into an injective one-way function generically. In fact, we know that there are some barriers and black box impossibilities there. Well, what we can do is take a one-way function and make it behave a little bit like an injective function. And this behaving like an injective function is going to be sufficient for us to be able to extract this, this hardness that we need to build a commitment. So in other words, there's going to be this tool that we use that's called a pairwise independent hash function. And the idea will be, and so what this pairwise independent hash function satisfies is that for every pair of x values, x1 and x2, the probability that a hash of x collides with the hash of y is, the probability that a hash of x1 collides with a hash of x2 is exactly 1/2 to the L. And so why is this helpful? Because it turns out that this function written here, f of x, along with the hash key h, along with the hash of the preimage x of an appropriate size, basically behaves like a one-way function. As long as the size of the hash function is roughly equal to the log of the number of preimages of f of x. So if f of x has, let's say, 4 preimages here, then if you take 2 bits of hash, this roughly behaves like an injective function. Why? Let's look at what a one-way function preimage distribution looks like. F of x, so f of x has, there's a few points that are preimages of f of x, and those are they're not all easy to find, and x is not arranged in ascending order, but we have a few points so every point is either a preimage or not a preimage. And the graph looks something like this. And moreover, if we truncate the hash to d amount of bits, then one can use the properties of pairwise independent hashing to prove that f of x and hash of x will have a unique preimage with good probability over the randomness of sampling the hash key. And moreover, it's going to be one way. This is because the hash of x will be close to uniform as long as they haven't hashed too much. So because this distribution is flat, meaning that every point is assigned the same probability, which is either 0 or the same non-zero value, this will give us that the min entropy of this distribution is equal to its Shannon entropy. And that will allow us to find a truncation of the hash that will make it so that we both have a unique preimage of f of x and hash of x, and f of x hash of x looks uniform. And this is the injectivity I've been talking about. So f of x, h of x both has a single preimage, and f of x, h of x is one way. So if you have both these properties, use the injective one-way function trick and get your commitment. The difficulty in the quantum setting is that one-way puzzles are not deterministic. And so every y in the image of the one-way puzzle does not have a fixed set of preimages. It actually defines a distribution over preimages, and this distribution is crucially not flat. So the fact that the distribution is not flat means that its min entropy can be much smaller than its Shannon entropy. And this poses a barrier to getting this injectivity type behavior that we want in order to get a commitment. The way we overcome this problem is that we focus on this flat slice of preimages. So we look at all the preimages, and we say that there's some region of preimages where the preimages are almost flatly distributed. What that means is that their probabilities are very close to each other within this slice. I'm labeling this slice G here. And what we show is that the existence of such a slice implies a form of pseudo-entropy. So more formally, what we show is that there is a distribution on the left, or there is one distribution that samples x and y and outputs y along with the hash of x and r and the inner product of x and r and so on, only if x is in the slice. And if x lies outside this good slice, we're just going to sample uniform values. So in other words, if you look at the distribution on the first bullet, it has less entropy than its size only when x is in the slice. So when x is in the slice, we're extracting this bit x dot r, which looks uniform but isn't. If x is outside the slice, we just sample random values. Now we can show that this actually turns out to be indistinguishable from a different distribution that just samples uniformly random values all the time. That's the second distribution on this slide. What one can show is that the two distributions are far in statistical distance, trace distance, and moreover, the first distribution has pseudo entropy. So what this means is that the total amount of entropy in the first distribution is less than the amount of entropy that it appears to have. So it's indistinguishable from the second distribution that has a lot more entropy. Okay, so are we done? We have these two distributions. They look alike, but clearly one is different because it has less entropy. So are we done? Well, unfortunately, we're not done yet. This is not a commitment yet because the first distribution is not efficiently sampleable because given a one-way puzzle pre-image X, it's not efficient to decide whether this is in the slice or not. So we're not done yet. However, what we are able to do is using this technique, we can go from one-way puzzles to generating pseudo entropy. And then from that, after a bunch of other manipulations, we can get pseudo randomness from it. And we get an object that is a non-uniform quantum pseudo-random generator. I'm calling it a pseudo-random generator, but there's a few asterisks. It's not the same definition of pseudo-random generators that you may be used to classically. So you don't want to claim that you get a pseudo-random generator yet. But you do get a source of pseudo-random bits. And you can then use an appropriate combiner to combine these non-uniform quantum pseudo-random bits to get a commitment scheme. So I'm not going to get into the details of all these steps. I just want to mention that there's a path from one-way puzzles all the way to commitments. I showed you the first step of the path. Sorry. And I now want to just say that in subsequent really nice work of Kai-Min Chung, Eli Golden, and Matt Gray, it was observed that a proof in an older work of Wadhan and Zheng can be tweaked to build commitments from one-way puzzles using a different approach than ours. And moreover, it also applies to weak and distributional one-way puzzles. So what is a weak or a distributional one-way puzzle? I'll give you one definition here, which is going to be relevant to the rest of the talk also, which is that there is a sampling algorithm SAMP that outputs pairs of puzzles and solutions such that given the puzzle string, it's hard to sample from the right distribution of solutions given the puzzle. Okay? So instead of saying that it's hard to pass some verification test, we're just saying you can't mimic the distribution that the sampler was sampling from. And this work also showed that weak or distributional one-way puzzles imply standard one-way puzzles. Okay, so now let's get to the question of why have I been boring you with all these details of one-way puzzles? Like, why are they useful? What kind of crypto can you do from them? Sorry, I've already told you what kind of crypto can you do from them, but these are just another fictional primitive hanging out in the ocean. And so sure, you can do crypto from this other fictional primitive, but why is this a useful primitive to look at? In the same work with Kabir, we showed that this object called a one-way state generator, which is again another plant hanging out in the ocean. It's this object which on input a classical key outputs a quantum state such that given the output quantum state, it's hard to recover this classical key. This was introduced in this work of Morimai and Yamakawa, and Tomoyuki talked about it briefly yesterday, so I'm not going to define this formally again, but I'll just say that there's this process called efficient shadow tomography that allows us to show that one-way generators imply one-way puzzles. So great, this one-way puzzle object gives us cryptographically useful things like commitments, and it's implied by other fictional objects like one-way state generators. In the same paper, we show that all of quantum cryptography with classical communication, basically anything that lets you get classical handles on the task that on a puzzle and a classical handle on the answer that would satisfy you. So that's basically all of quantum cryptography with classical communication also implies one-way puzzles. And this work of Chung, Golden, and Gray that I just talked about on the last slide shows that weak versions and distributional versions of this one-way puzzle primitive also imply the standard notion where you need to pass some verification test. Okay, great. So one-way puzzle is implied by all these things, but it's still floating around in this vast ocean. We don't have any grounding for it. what concrete assumptions, or either complexity assumptions or mathematical assumptions, can we use to get any of these primitives. So now I want to get to the second half of the talk, which is about trying to build these one-way puzzles from concrete assumptions weaker than one-way functions. And so in an upcoming work, we show that as long as there is sampling-based quantum advantage, then sharp P hardness essentially implies the existence of one-way puzzles. So let me explain what this is. I'm going to parse that statement in a bit, but basically, let me start by saying that one dream is to try to build quantum cryptography from sharp P hardness. What is sharp P? Sharp P is a counting complexity class. It captures the complexity of answering the question, how many satisfying assignments does a particular Boolean formula have? And one-way puzzles is a primitive that is known to break to a sharp P oracle. And there's a beautiful work showing this that I should have cited here, I'm sorry. So they exist only if BQP to the sharp P is not in BQP. And so one-way puzzles necessarily require sharp P to be hard, but is this assumption sufficient? Can we build one-way puzzles from sharp P hardness? This would be cool because one, it would show that quantum cryptography can be based on sharp P hardness, which is way weaker than NP hardness, which is necessary for classical cryptography. We're not going to be able to do that yet, although it's an intriguing open problem. But to try to understand this scenario a little bit more, let me give you an example of a sharp P complete problem. So the permanent of a matrix is this value that looks at a matrix. It's like the determinant, but without signs, basically. And it's this sum of products of entries taken a certain way. And this is actually sharp P hard to compute in the worst case. So in the worst case, for asymptotically, this problem is sharp P hard. And actually, really nice thing about this is that it's also hard in the average case. So permanents have worst case to average case reductions, which is wonderful. This is something cryptographers look for all the time, is for average case hard problems, and this comes for free with permanents. So can we try to build cryptography from the hardness of computing the permanent of a given random matrix? And this problem we know is sharp P hard, no extra assumptions needed. Well, let me also point out that solving this classically, like if you could build classical cryptography from the hardness of computing permanents for a given A, then you'd basically be collapsing the polynomial hierarchy. So we don't expect this to be possible classically. Okay, so let's try to do this. Our task is permanent, computing permanence is hard. Let's build crypto from it. The issue is the following. One-way puzzles crucially need to have an efficient sampler, because crucially, commitments need to be efficiently computable. We actually do need our honest parties to be able to commit efficiently. And so if the puzzle sampler needs to be efficient, that means if you're using permanence as a first step, it seems like you should be able to efficiently sample a random matrix A along with its permanent. And there's significant complexity theoretic evidence that this may be hard. So this appears unlikely. And we tried for a bit, but it seems like a random A cannot be quantumly efficiently sampled, or we believe that this is going to be hard to resolve. So we don't have a puzzle that looks like this, given a matrix A, computed permanent, it's going to be hard. Actually, if you could do this with a classical sampler, you'd have a one-way function again, and so we don't expect that to be the case. But we actually also think that a quantum sampler sampling matrices together with permanents is unlikely to exist. Okay, so which brings me to this connection with quantum advantage that I mentioned on the theorem slide. So in these beautiful works on trying to prove sampling-based quantum advantage in the near term, it's been observed that quantum computers can efficiently sample from distributions such that for that particular distribution, the probabilities of outputs assigned by that distribution to values X encode permanence of certain matrices. And if permanents are hard to compute on average, then that actually implies that these probabilities of outcomes of these efficient quantum processes are going to be hard to compute on average. So instead of trying to directly compute permanents, we're going to focus on trying to compute probabilities in the rest of this talk. Okay, so for a random x, it is hard to compute the probability of x. This is what we know from the hardness of computing permanents. Of course, this is only true in the exact case and so on, but I'll come to that in a minute. Okay, so this gives us an idea. Again, the first idea is let's sample our one-way puzzle and solution pair as some random x. The solution is going to be the probability of x. But clearly, this is, again, going to be hard to sample because we don't know how to sample x together with the permanent, and that's essentially what this problem is encoding. So this is basically the same issue as the previous slide written in terms of probabilities. So all that is easy to sample is a random x from the distribution x. Okay, so how to use this to build a one-way puzzle? Well, it turns out that the following is a distributional one-way puzzle. We sample a random x, say x is n bits long. We sample a random I from 0 to n minus 1, and we output the first I minus 1 bits of x as the puzzle, and the ith bit of x as the solution. So the hard task is going to be, given the first I minus 1 bits, sample the ith bit from the right distribution. Okay. Here's an oversimplified proof of security of this. I'm hiding away many, many things here. But let's assume that we have an adversary that, given an input string x1 through xi minus 1 for every I, samples xi perfectly from the exact right distribution. Okay, this distribution is this distribution capital X, which is sampling instances small x. And what we're going to try to do is use this machine A to compute the probability of x appearing in that distribution. So say that the string x is 0, 1, 0, 0, 0, 0. We're going to run A on the value bought many times to approximate the probability that the first bit is a 0. Now we'll feed A the first bit 0, and again run it many times to approximate the probability that the second bit is a 0. To approximate the probability that the second bit is a 1, because that is what we want here. Now we'll run the adversary A on string 0, 1 many times and approximate the probability that the next bit is a 0, and keep going. Okay? So you would have noted that on top, I've been saying we're going to compute the probability of x. Here, no matter what we do in polynomial time, we're only going to be able to approximate things. And so what we did was, given a machine that on input, the first I minus 1 bits samples the next bit perfectly, we built a machine to compute the probability of any given string x up to some errors. When the machine A is a distributional puzzle inverter, basically if that object where you sample a long string, truncate it to the first I minus 1 bits, I'll put that as the puzzle, I'll put the next bit as the solution. If that candidate is, as long as that admits an inverter, we are actually able to compute the probabilities of any given x. But when defining one-way puzzles or even distributional one-way puzzles, the adversary is allowed some margin of error. So the adversary doesn't have to exactly sample from the right distribution. It's allowed to sample from distributions that are a little distance away. It turns out that you can spread the error that the adversary makes across all instances x, so that on average, it is still possible, for most x's, it is still possible to approximate the probability of x with low error. This imperfect case, like I said, requires a lot more subtlety and work than the perfect case that I illustrated. But so I'm not going to be able to show this today, but the preprint will be out soon. So I encourage you to look at it if you want to see a proof. So I want to clarify now, what is it that we assume? So the assumption is that quantum computers can efficiently sample from a distribution x such that the probabilities of particular strings little x are hard to approximate on average, up to inverse polynomial multiplicative errors, and that not all of these probabilities are too small. So this is, for example, implied by conjectures in sampling-based quantum advantage. Let me list a few. So one of the initial works that observed this connection was in the setting of boson sampling. This work of Aronson and Arkhipov showed that permanents of random matrices with Gaussian random entries are sharply hard. Sorry, I said showed. Let me take that back. The work of Aronson and Arkhipov on boson sampling showed that boson sampling is a viable candidate for quantum advantage under the following assumption. The assumption was that permanents of random matrices with Gaussian random entries are sharply hard to approximate on average. Now, wait a minute, I just said that permanents are actually hard to compute on average. Here I'm saying this is a conjecture. Why is this a conjecture? Why don't we already know this? Well, because you're only getting an approximation here. So making approximations in the worst case is hard. Computing exact permanents is hard. But computing approximate permanents is, we do not have a proof that this is sharply hard. So this is only conjecture. There's also similar conjectures in random circuit sampling, where a lot of the complexity theoretic evidence for why random circuit sampling outcomes give us quantum advantage is based on a conjecture that the output probabilities of random quantum circuits are hard to approximate on average. And there's other models like IQP, DQC, et cetera, with similar properties. And any of those properties will basically imply the assumption we want. So take your favorite model of quantum advantage, and it comes with this assumption about the sharp P hardness of a certain approximation, output probability approximation task. And that's exactly what we need to get the existence of one-way puzzles. So if there exists an efficiently sampleable distribution such that you cannot approximate individual outcomes up to arbitrary inverse polynomial error, then this is equivalent actually to the existence of one-way puzzles, which as a consequence, I would say, shows that there's these seeds of DQC, random circuit sampling, boson sampling, IQP, all of these tasks for which there have been conjectures that have been studied. People have tried to refute them and failed. People have been trying to prove them for a while now. But there are these conjectures about sharp P hardness of particular mathematical problems that imply the existence of one-way puzzles, which in turn imply commitments and MPC and so on. Another consequence is that one-way puzzles are actually implied by non-universal models of quantum computation. So boson sampling, for example, and IQP and so on are not necessarily universal. And this gives the possibility of building quantum cryptography, maybe in the near term. I'm not claiming that we do this. It's just maybe this is a possibility to be explored in future works. Also, it turns out that a host of other quantum search problems imply commitments. So one-way state generators is one example. State puzzles, some types of fully quantum search problems are other examples. Let me give you one small example. So a state puzzle captures the hardness of generating a quantum state that's secret given a public string S. So there's a sampler, it outputs S and psi S pairs. And the hard task, the task that is computationally infeasible, is you're given S, you have to find psi S, or basically synthesize a state that has some non-trivial overlap with psi S. And what one can show is that what we show in this work is that state puzzles imply one-way puzzles, which imply commitments. And this proof needs a fair amount of work. I'm not going to be going over it. I'm also almost out of time. But I want to just point out that this proof needs a fair amount of work because, but it uses the equivalence between one-way puzzles and the hardness of approximating probabilities in a crucial way. So some additional consequences are that one can amplify state puzzles generically. One can amplify the hardness of approximating probabilities generically, just because these things seem to be equal to one-way puzzles and we have nice amplifiers there. So also, it seems like one can generically amplify the hardness of classically sampling from quantum distributions. So if you have a quantum distribution that no classical sampler can get inverse polynomially close to, then you have a different distribution that no classical sampler can get even slightly close to. So, And in conclusion, I just want to say that quantum crypto systems can actually be based on what I think are nicer, weaker assumptions than their classical counterparts. In fact, if these assumptions from quantum advantage turn out to imply one-way functions, then what we're doing in quantum advantage will all break apart. So then quantum advantage does not exist from these assumptions. So we do not expect them to imply classical cryptography. And so I want to conclude with one main question, which is for commitments in MPC, have we hit the ceiling with sharp P hardness, or can we weaken assumptions further? And do we need any unproven assumptions at all, or can we maybe get commitments secure against computationally bounded adversaries, but without having to make any unproven assumptions? That would be really cool, I think. And with that, I want to conclude. Thank you.
Questions?
Thank you for nice talk. So you constructed one-way puzzle from the assumption that quantum machine can sample some distribution. And do you also assume that this distribution cannot be classically sampled? Because otherwise, from your assumption, you can get one-way function from that.
Good, yes. So we assume that these tasks are sharply hard. That's it. So we assume that the probabilities of computing, so we assume that the probabilities of individual outcomes are sharply hard to approximate on average.
Yeah, but what happens if your distribution is also classically sampled?
So if the distribution is also classically samplable, then these probabilities cannot be sharply hard, right? That's what the quantum advantage thing relies on. They say that if it is classically samplable, then the polynomial hierarchy collapses to the third level. So we actually do not expect them to be classically samplable. And so what we need for the existence of one-way puzzles is that it's BQP hard to find these probabilities. That's the minimum thing we need. But what I'm saying is that it's actually conjectured to be sharply hard, which is way weaker than one-way functions.
But so what you need is, so you can not classically sample in additive error.
So if you could classically sample, I think that basically means that this gives a one-way function, which also gives a one-way puzzle. So this is like another way to get a one-way puzzle from a one-way function is to build this classically samplable distribution whose probabilities are.
Maybe you want to do that.
Sorry, maybe you want to.
Maybe you want to construct a one-way puzzle from some assumption which will not imply one-way function.
Yes.
So maybe you want that this distribution is not classically samplable.
Good, yes. So if the distribution is not classically samplable, then you have a one-way puzzle from an assumption that does not give you one-way functions. If the distribution is classically samplable, then you have another route to getting a one-way puzzle from a one-way function, if that makes sense. Yes. Thank you.
More questions? So classically, there's this other route to get one-way functions like this homograph complexity. Do you think that this can, like something like this could be done in the quantum setting?
I haven't thought about it honestly, but I feel like it has to be connections. We just haven't discovered them. So, yes.
Thanks for the nice talk. So you wrote an open problem in one of the initial.
Yes.
I mean, it's okay. You don't need to go back. But so you said it's an open problem to, from commitments, get secure quantum computation with classical communication, if I understood correctly. But do we know other assumptions that give us this quantum computation with classical communication?
So good. So the question is to build secure computation of classical functionalities by using quantum resources. So we do know how to do this using just classical resources from stronger assumptions. I should have maybe mentioned that, but if you remember these gardens, let's see. So you have MPC there on the very left. So we know how to do it from assumptions like DDH, RSA, factoring, even LWE, and so on.
Thanks.
Yeah, no. In the second, a very basic question, I guess. In the second half of your talk, you said that you want to construct cryptographic protocols from the assumption of sharp P hardness versus P. Then you went via the route of the random circuit sampling or random boson sampling, which relies on the hardness of approximating these things, which will be in BQP. So would it be fair to say that what you actually construct is cryptographic primitives based on the assumption of BQP hardness, like BQP versus P?
So ideally, if there existed some assumptions, well, I shouldn't call them assumptions. If we knew that there is some distribution such that computing its probabilities is hard for BQP polynomial quantum advice, so PQP/Q poly. If we knew that this were the case, then we'd be done. We wouldn't need to make any assumption at all. So what the goal is to see if there are assumptions weaker than NP hardness, say, where like you're actually conjecturing that this task is harder than NP, and to try to build crypto from them. And so this is like one step towards that goal is to say, well, these conjectures in quantum advantage are about sharp P hardness. And they actually conjecture that random circuit outputs are sharp P hard to approximate. And so that also, assuming that sharp P is hard for BQP, and assuming the conjecture, one gets quantum cryptography.
Okay, thanks.
Thank you.
Okay, I have another question. So at some point in your, like you had this non-uniform part in your, like, so the non-uniformity does not translate up to the end, like the commitment is uniform at the end, right?
Yeah, it is uniform at the end. Yes, so the intermediate object, the pseudo-random object we get has some non-uniformity in it. We don't know how to remove that non-uniformity and get a PRG. Interesting open question. But what we get is we can get a commitment without any non-uniformity. Yeah, I'll have to scroll a bit to get to that.
Getting a PRG would be too powerful, right? Because then it would imply that it would be equivalent to 1A functions.
Great, yes. Yeah. So PRS maybe, like some version, I don't know, PRG, yes, absolutely. Getting the standard definition of a PRG would be too powerful. I shouldn't have said that. Some type of pseudo-entropic generator that's maybe not deterministic necessarily. What we get is like a weird weak object that's not worth pointing out as its own primitive, I think. But the final thing is we get a commitment without any non-uniformity.
Any further question? If not, let's thank Dakshita again.
Thank you.